So this week's tutorial will be discussing the assignment. So if you have any specific questions or any bit that you're not quite sure about, or one of the analysis doesn't quite make sense, please let me know now so that I can focus on that in this tutorial session. I hope you've all had the chance to start the assignment. Just let me know, so I have a rough idea. What's the progress so far? You guys starting with the calculation report, halfway, finished doing the drawings, finished both? What's the status? Okay, so hopefully you're all have started. Is there anybody who hasn't started the assignment yet? This tutorial will be driven entirely by you guys. So whatever you have problems with is what I'll discuss. So you have to let me know what you'd like me to discuss. So while you guys think about that, I have a few questions for you guys. And they're based on the assignment and also a bit of engineering theory, since this is the assignment that introduces you to what is to come, especially if you're a mechanical or civil engineer. Okay, Va, your problem is, sir, I've done my calculations, but the radius of the bolt was too small. If I increase the radius, the number of bolts will be less than 4. Right, my radius of bolt is 1.5. So what's wrong with having less than 4 bolts? There's no limit as to how many bolts you can have. The minimum that you can have is 2. Right? You need at least 2. So even if you reduce the number of bolts that you have, that's fine. So long as so even when you do a calculation with 2 bolts, what is your bolt radius? Have you done that yet or not yet? The other issue you might be having is maybe you've made the radius of your hub, or maybe you've made your PCD too big. Maybe your PCD is way too big, and that's why you have very little force, so small bolts only. That would be the other explanation. Well, that would be the only explanation, that your hub diameter or your PCD is far too big. So I'll talk about the bolt analysis. Are there any other analysis that you guys aren't sure about? So I'll talk about I'll do the bolt analysis and the hub analysis. Let's talk about those two. All right, so before we begin, I want to talk a little bit about the engineering theory behind what this whole assignment's about. Okay, so this whole assignment is basically we're trying to size a component based on the forces that it will experience during its working lifetime. Now we're given a flange coupling, and we have to try and size it appropriately for the amount of power that has to be able to transmit from one shaft to another. Right, we're given all that information in our assignment brief, design brief. Okay, so before we jump into that, what are the types of forces that we might experience? What are the types of forces that we engineers have to account for? In this assignment, there are 3 types of forces, but there are many more. This is just to see whether or not you guys are understanding the basic theory before you jumping into the calculations or not. So what are the 3 types of forces we can generally come across? Yes, one is tensile. Shear force is another, yes. And compressive, very good. So tensile and compressive are normal forces. And shear is the odd one out. By normal forces, I mean if we're looking at a component, let's say a round rod, and we apply our force, the force is acting normal or 90 degrees perpendicular, whatever you'd like to call it, to the surface that we're interested in finding the stress on. So it's a normal force creating a normal stress. Shear stress acts parallel to the surface, and it causes a sort of slicing motion, or makes the different layers of the component want to try and slide against each other. That's called a shear force. So yes, we have 3 types of forces. Tensile is trying to pull the element apart and try and make it stretch. Compressive is trying to squash it together, and shear is trying to make it slice. Second question, how do we tell if our design is adequate? When do we know that our design will work? Right? How do we know when we have sized our component correctly? So as engineers, especially design engineers, there are 2 things that we have to keep in mind. First one is safety, and safety is always paramount. Safety is the #1 priority. Second one is cost. We have to make sure that our designs are cost effective as well as being safe. Safety for the public, for the customer, for the client, cost effective for the stakeholders, the investors, our companies, what have you. Right? So we have to try and satisfy both sides and make sure that our design hits a sweet spot between the 2. So usually, if you try and make something very safe, it means you have to invest more money in it. It'll be more expensive. And sometimes if you try and cut costs, your safety can be compromised. So that's the whole idea when you're trying to design something. That's why when we say in your project, it's very good to include a cost aspect to your design criteria, because cost is always something that people are very interested in. Cost and safety. Right. So hopefully you're all familiar with this stress strain curve. And this is the stress strain curve for ductile materials. So mild steel, aluminum, they all have stress strain curves similar to this. And each material has its own stress strain curve. Now the stress strain curve shows the relationship between the stress and the strain. Basically, let's look at our component again. I'm experiencing some force. So as we increase the force, the stress will increase. And as the stress increases, the strain increases. That is only true in this first region here. This region is called the elastic region. And in the elastic region is where we usually try and work, because we know that there is a definite relationship between the stress and the strain that our part will experience. Now, stress is the amount of force per area, and the strain is the change in length, or it's a change in shape with the increase of stress. So Mechanical and civil engineers, this is sort of grassroots stuff for you guys, and you'll use this all the way through your next 4 years and then jumping into industry. This is the basis of everything that we do, pretty much. Stress and strain, the relationship between the two. There is a point up here where the direct relationship no longer exists, and this is called the yield stress. The yield stress is the maximum stress that the material can withstand without changing its shape. As soon as you increase the stress higher than the yield stress, your material starts to enter the plastic region. And the plastic region is where you have permanent deformation. By permanent deformation, I mean, if it changes its shape, it won't go back to its original shape. Right? And this is usually termed as a failure. So when we design parts, we design components, we try and make sure that during its working life, it will never change its shape. So we always try and have a working load limit, or the maximum load that the material will experience when it's working, to be less than the yield stress. Okay, so that is how we know whether or not our design is adequate. If the maximum stresses experienced are less than the yield stress of the material. Now, can anybody tell me what the factor of safety is? What is a factor of safety? What is the factor of safety? Now, the factor of safety is the direct relationship between the yield stress and the maximum working stress. Okay. It is the ratio between our maximum yield of the material and the maximum working stress of the component when it's performing its function. Now, a factor of safety of 1 means the yield stress is equal to the working stress. And generally, this is advised against. Okay, we don't want this. What this means is we don't have any margin for error or any room for error. If we have, some kind of anomaly, like there's some kind of impact force, or our shaft suddenly gets some surge in load and it starts to generate more power than it should, it'll mean our part will fail. So we always try and work to a factor of safety greater than 1. So a factor of safety 1.2, 1.5, so on and so forth. You can go up to 10, 100, what have you, so long as it's greater than 1. Now, these are all industry standard. They're based on the application and the material. So if you're using a very reliable material, which has a lot of data, we know for sure what its yield strength is. We know it for sure its properties, and we know for sure the types of load that it will experience. We will have a lower factor of safety because there are less unknowns that we have to account for. When people's lives are at risk, say a bridge design, you would have a higher factor of safety because people's lives depend on your design. So you wouldn't want to have such a small room for error. You probably go for a factor of safety of 2 or 3, 4. Larger factors of safety, so for when we don't know the material or we don't know the types of loads that it'll experience. And usually huge factors of safety are advised against. And why is that? It's because as we increase our factor of safety, it'll mean we will either have to add more material or we will have to change material to be something that is stronger and usually more costly. So it's again trying to find that sweet spot between safety and cost. And that's basically what the factor of safety is. Now jumping to your assignment. Your assignment is broken down into 5 different analysis types. We have our torque analysis, key analysis. We have our hub analysis, web analysis, as well as our bolt analysis. And the order that you do these in is dependent on the load path. So the critical load path that we know is we have our part A and part B. We're trying to rotate part B at the same power and with the same torque as part A and torque. And we're trying to get part B to have the same power and the same torque, right? And to do that, the forces have to travel from the shaft, which is rotating, to the key, to the hub, to the flange, to the bolt, and then out the other side. So that's the reason why we do the analysis in that order. We go shaft, key, hub, flange, bolt. But for this assignment, we don't have to worry about the shaft because the shaft is already given to us by the client. The client has already said that they want to use a 48mm shaft. So we start our analysis from the key analysis once we've determined our torque. Right? So the outcome of the key analysis is to find your key length. The outcome of your hub analysis is to find your hub thickness and then your hub diameter. Outcome of your web analysis or your flange analysis is to find your flange thickness or web thickness. And your bolt analysis is to find the number of bolts and the size of bolts that you're going to use. All right, so I'll now talk a bit more in depth about the bolt analysis. And if you have any other questions about any other of the analysis types, I'll go over those as well. So the first step when you do your bolt analysis is to come up with your PCD. Now, PCD is called your pitch circle diameter. Pitch circle diameter. What is the pitch circle diameter? It is the distance from the center of your bolts on one side to the center of your bolts on the other side. Okay, it is that distance. And your flange is round, so it'll be a circle, hence the term diameter. Now your PCD is governed by two things, and the PCD will vary for each one of you. You will all choose a different PCD, or some of you might have the same, but you know, this is completely up to you guys, and this is where you apply your engineering logic or your designing logic to come up with this number. So obviously, let's say that this inside circle here is supposed to account for your hub. So this is your hub diameter, right? Your hub goes inside here, your hub. So your PCD obviously has to be greater than your hub diameter. But then what's left over is the distance from the outside of your hub to the center of your bolts. That distance there, let's call it A. And that distance is the one that's up to you guys. So your distance A is dependent on accessibility. So remember, we're talking about bolts. Bolts need to be tightened and loosened to fit and then remove. So you have to leave a sufficient amount of space between the outside of your hub and the hole for your bolt for you to be able to get your hand in there to fit a spanner or fit a wrench and then tighten and loosen. Right? So you can't make your hole too close to the edge of the hub because then your bolt wouldn't fit. You know, your bolt head would be pushing against your hub, but you also can't make it so that you can't make it too big because then you start to waste material. You start to make your part, you know, bigger than it actually needs to be. Stuff like that. All right. So your PCD is equal to your hub diameter plus 2 times the distance A. 2 times because A is this side as well as this side. Following so far? Okay. You could also determine your PCD by looking at your bolt dimensions up here. And this gives you the basic sizes depending on the size of bolt that you use. So if you know that your bolt will protrude, so your bolt head will protrude by this much from the edge of your bolt or the center of your bolt, you have to also account for that distance in your PCD. So generally, if you work with a PC or with this assumed distance A of anywhere between 30 and let's say 50, if you work with a PCD anywhere between those two dimensions, 30 and 50 millimeters, that's usually appropriate. But you could also do a bit of research into how much space you should leave when you're trying to design a flange coupling. That information is on online as well. Different products, they have different PCDs. You could use some of those to help come up with your PCD. But generally around 30 to 50 millimeters is acceptable. Once you have that dimension, you plug it into this formula and you can solve your PCD. Does that answer your questions about PCD? Okay, great. So now, like for each of these different analyses, we have to find the force. Okay, so at the center of the shaft, our force is maximum. As we get further away, our force will decrease. And that's because the relationship between force and distance is inversely proportional when torque is constant. So we already found our torque from our torque analysis, and we're trying to find the force. The distance will be the distance from the center of the shaft to the center of your bolts, which is basically your PCD divided by 2. And making force the subject of the formula, we can find our force. Now, can anybody tell me what type of force we'll be experiencing on these bolts? What type of force will these bolts be experiencing? Shear, compressive, tensile, which one? Shear force, yes, exactly. The rotation of this coupling is trying to twist these bolts, which creates sort of a slicing action, and we have a shear force. So using that information, when we try and go and solve for our stress, our shear stress will be equal to the shear force divided by the area. This area is the total area of the shearing surface. Area is equal to the area of each bolt. So these have a circular cross section, and the area of a circle is pi d squared over 4. And you have a certain number of bolts times number of bolts. This is how you solve for your area, this formula. Pi d squared over 4 times the number of bolts that you use. We've already solved for our force. We just don't know our shear stress. Now the shear stress we can get from the question itself. Now this bit of information here is about the bolt that we'll be using. It gives us the property class. It gives us the ultimate tensile strength and the tensile yield strength. But remember, we're looking at the shear force, so we'll be interested in the shear strength of the bolts. That isn't given here. However, if you read through and you have your information about metric bolts, this table, and then you read this second paragraph, it says the allowable shear strength of the steel fastener is about 0.66 times that of the tensile yield strength, which means our shear strength in this formula, our shear strength is actually 0.66 times the tensile yield strength. And we know that the tensile yield strength is 240 megapascals. So our shear strength comes to be about 158.4 megapascals. This is the value that we'll use in this equation. We will use this force here, and we'll use this area here. So when we write it up again, it'll look something like this. Now we know shear stress, shear force. We don't know the diameter, and we don't know the number of bolts. And this is where you make the decision. Either, there's two ways you can go about it. You either state the number of bolts and then solve for the diameter, or you state the diameter and solve for number. There are two ways you can go about it. You could either say, I want to use 4 bolts, but I don't know the size. Or you could say, I want to use a size 12, so M12, meaning 12 diameter, but I don't know how many I want to use. So depending on how you want to go about this, you can rearrange your formula appropriately to be able to solve for either. Okay. So let's say I want to use 5 bolts, but I don't know the diameter. So I plug 5 in here, I make D the subject of the formula, and I come out with a diameter of 13 millimeters. Let's just say, for example. Now, using this information, I'll go back to my table. And I'd look for M13, diameter 13, so M13. Now, M13 falls in between M12 and M16. So obviously, I can't use M12 because if I use M12, my part will fail. So I have to use the next one up. So I would use M16. So once you finish your bolt analysis, you would end with a statement like M16 by 5 at PCD of, and whatever PCD you stated up here, say 250 mil. And that's how you would end your bolt analysis. Okay, any questions? Any questions? Okay, great. So this session will actually end in 7 minutes. So if you would like me to cover the hub analysis, I can end this session and start a new one join using the same login information as you did to join this session, if you'd like. So just let me know in the chat whether or not you want me to cover the hub analysis or not. Okay, great. So I'll end the session now, and I will start a new session. At the end of that session, I will be taking attendance, so please attend that session.